Hi, my name is Jeff Moore. I'm one of the founders of Embedded Now. We make a variety of small, powerful embedded computer systems. And lately, we've been doing a lot of work with SDRs and GNU Radio. So I hope to share with you some of the design challenges we've had and some of the insights we've gained in using this type of hardware and software. So thank you for coming to the talk. I hope you enjoy it. Believe it or not, we're going to try to do it all in 30 minutes.
The first thing we're going to talk about is platform. This is the issue of Intel/AMD or x86, x64 versus ARM. And there's really a huge conundrum if you think about this. Intel and AMD processors are designed to be used in laptops and desktops. The performance is huge. You know, they are really the king, but the power consumption is, in a matching way, very large. Software compatibility is good. Product lifetime, though, is planned to be obsolete from a marketing and even a technical perspective. Some of these chips simply do not last very long. If you run chips very hot and very hard, like a lot of times when you do in desktop and laptop processors, and you don't cool them well enough, they literally die. And I know I've had experiences where my processors died or other chips have died inside my laptop because I did too much too long. And also the chips tend to be expensive. The Intel and AMD chips are expensive, typically $40 or $50 just for the IC itself. ARM processors, on the other hand, are designed and built for embedded solutions. Their power consumption is relatively low. The software compatibility is pretty good, but less than Intel and AMD. And the chip life is much longer. And not just from a technical perspective, how long does a chip last, but from a marketing perspective, how long does that company make that chip so you can use it in a product, in an embedded product. And typically in embedded products, we look for product lifetimes of 5 to 10 years minimum. So the Intel and AMD world provide a much higher performance than the ARM world, but the ARM world really won't work for many applications, especially involving GNU Radio and these kind of DSP applications. So what do we do? So most applications need the performance and software compatibility that Intel and AMD provide. You have to choose the processors carefully. Intel has literally hundreds and hundreds of processors. It's mind-boggling. And every year there are new ones. And then every year there are new ones planned for the following year. They have this whole chain of processors that are always coming out. And that reflects the consumer orientation that they have of desktop and laptop environments. Also, when you buy a platform or a processor for an embedded environment, you really have a choice as a designer and as an engineer. You can buy the raw SoC, the system on a chip processor, like you see on the left here. This is an AMD Ryzen embedded processor. Or you can buy that chip mounted on a module. And there are many types of modules. You may have heard of ComExpress or SMART or Q7. You know, there are many different types of standards that modules come in. And the idea with modules is that the manufacturer of the module has done all the very hard work of putting that SoC, that chip, onto a board that can then be plugged into a system. Okay, all the RAM, all the really intense power layout and power management for a chip is done on that module. And it's no easy task as an engineer to design around these SoC chips. For example, Intel and AMD both have features, I call them features, where the actual supply voltage, one of the many supply voltages to the chip is variable, but extremely high current. For example, AMD Ryzen takes a nominal 0.9 volts at between 50 and 75 amps. That's huge. But that 0.9 volts can vary by quote unquote software control from the chip between 0.75 or 0.8 volts and 1.1 volts. And it's the firmware, I don't even know if you call it firmware, but the silicon in that chip that decides what voltage it's going to run at. And that's how they try to manage power and boost performance. So if the chip decides it needs to boost its performance, it may juice up the voltage to 1.1 volts and really crank up the amps. So there's a whole set of circuitry that you have to support around that chip in order to do that. And the chips that do that power management are usually only made by one or two companies in Asia. And sometimes they're hard to get and they won't sell to small companies or even medium-sized companies. They'll only sell to giant companies like people who like Asus or somebody who makes, lots of desktops and laptops. So it's very hard to design an embedded system around a SoC. It's doable. We've done it, but it's very difficult. And then some of those chips go obsolete and some are difficult to find over time. So what we tend to do in general is use a modular approach. And that's the modules you see on the right. And all that hard work is done for you by companies who make those modules. Now for CPU performance, it's really interesting. If you look at the Intel line in particular, and you look at the performance specs, they are all really close to each other for the last few years, especially. Yeah, you can have more cores, you can have more threads, you can have higher processing rates and frequencies, but clock rates. But if you look at the performance, they're not that far off. Now, certainly an i3, i5, i7 are more powerful than Celeron, what they call Celerons and Atoms and that class of processors. But by and large, within the class, like amongst the Atoms, for example, they're all very, very similar. Amongst the i3s, they're very similar. Amongst the i7s, they're similar. The number of cores does matter. We've seen a lot of situations where more cores really does make a difference. And in particular, GNU Radio divides well amongst the cores without having to do a lot of manual work to make that happen. So a 4-core processor will run something in each core 1/4 of the amount of time it would take a single core to do. So that was very interesting and nice to see. So the performance itself is really, you can look at frequency and you can look at level 1, level 2 caches and how many threads and what the GPU is doing. But by and large, you really got to test this. Test it with your particular OS, your version of GNU Radio, and your application and see what works. We've not found any substitute for that. One element of performance has to do with data latency and jitter. And what is that? Latency is the delay between when you want to sample data from an SDR and the actual time that you actually do sample that data. And jitter is the variability of that latency. And you've really got to minimize both because it can cause errors and inconsistencies in the sampling of the data from the SDR, which causes all sorts of, it can cause aliasing, of course, but it can also cause lost data and inaccurate calculations down the line from that. And the only way we've found that we can solve that is to architect around it. You can try to throw more performance at it, and some people try to do that by just upping the performance of the CPU so that you minimize the O's. Like everybody knows about the O's, the overflows. But if you architect around it and try to thread things so that data collection is in a different process than data processing and at a higher priority, you can minimize the amount of performance that you need in a CPU in order to meet the needs of your application. In an embedded environment, data storage is always an issue. There are many ways of doing it. You can use flash memory, which are actually just IC chips, laid down on a board. The flash memory chips itself. You can do a USB memory stick. You can do a SATA drive, either an external drive with a SATA connector on it in your enclosure, or you can do an M.2 format type drive, which is a little board, or an NVMe drive, which is PCIe format interface in an M.2 format. The speed, the reliability, the capacity are all an issue. But most importantly, in an embedded environment, it's the life of the silicon. All flash drives, NAND drives, all these semiconductor types of memory have limited lifetime. You can write to them only a certain number of times, measured in the thousands or tens of thousands Okay, so you have to architect your system in a way so that you minimize doing that. Now, many drives will have extra space on the drive and will intelligently skirt around areas that have been written to too many times and start to wear out, and that's all invisible to you. But there is a limit to how many times it can remap itself, which means there's a limit to the life of that particular component in the product if you're writing to it frequently. So you either have to write to it infrequently or not load the drive very heavily. For example, if your application typically writes 100 gigabytes of memory on some frequent basis, you might want to have a half a terabyte drive in order to have that much extra room, or architect it in a way that you don't have to do that. Okay. This just shows one of our products that has an M.2 format of an SSD laid down on the board. This is a 500 gigabyte. This is actually a terabyte version, and we tend to use the name brand SSDs, Samsung, Intel, for example, up until recently, Crucial. There is a lot of variability in the quality and the integrity of many of these products. So we tend to use the better name brands and pay a little bit more for them. And we get the benefit of higher reliability and less issues down the line. In an embedded environment, physical size is always an issue. We make a variety of products. This is an example of one of our smaller ones. This is 95 by 55 millimeters. We make others that are a little bit larger or, similar size. But one of the issues when you make something this small is you have to get rid of the heat. You see this little blue anodized aluminum plate on top of this product. This is called a heat spreader. You would typically mount this to a chassis or even the enclosure of your product, where this board is inside the product. And that aluminum plate is thermally connected to the chip, to the hottest chip or chips on the processor module. And this is anodized aluminum because anodized aluminum is actually has better heat transfer characteristics than raw aluminum. But this means your outside enclosure can't be plastic, for example. It should be metal, or at least the part that joins this should be metal. And you have to do calculations to make sure that the heat that this generates is shunted to the outside world and dissipated. Otherwise, you have this sitting in a box and it's like a little oven. And even though this board may only draw 5 to 7 watts, or in worst cases, 15 to 20 watts, it's going to get really hot in there if you can't get rid of the heat. This is another one of our boards that we did custom for one of our customers. This may look familiar to some of you. This has got 2 of the Edis Research NI USRPs, the B200Is. This is an industrial version of it. The little board off to the left is a little Wi-Fi Bluetooth chip. And in this situation, they had to have this many radios, and they had to have it mounted on the board in this way in order to provide the physical integrity. You see on the underside of the same board, you see the SSD. We mounted that far away from the radios and on the opposite side on purpose for EMI reasons. You also see, this is just a temporary on my bench of a heat sink sitting on top of the heat spreader for this particular module. This one, I believe, is an AMD Ryzen mid-range kind of processor. And the little aluminum package that you see down front, it's not aluminum, it's actually tin-plated copper. That's a shield over a GPS chip. So we've talked about heat dissipation a little bit. Heat dissipation is important to get rid of, as we talked about in relating to size and the enclosure. But the main trade-off in any of these designs is usually between processing horsepower and heat. The more processing horsepower you need, generally the more heat that is produced. Okay, it also affects battery life tremendously. And most of these products that you build that are embedded have to run without a fan. They don't want a fan because of environmental applications where you can't be exposed to liquids or some kind of environmental situation, and a fan is not compatible with that, or they don't want the limited lifetime and failures that fans introduce, okay, because it's moving parts. They will not last forever. So almost everything has to run without a fan, which means you've got to get rid of the heat. EMI, electromagnetic interference noise generation. This is particularly important in SDR related applications, and it's important in all products because there is the FCC and other government regulation organizations that regulate how much EMI you can generate. But in an SDR world, because we have these highly sensitive radios, you do not want the noise that all this fancy digital circuitry generates to be picked up by these SDRs. So you've got to be very careful in your design of how you lay down the digital logic, where you locate it with respect to the SDRs and how the SDRs are shielded, etc. We use ground planes and proper impedance transmission lines for all high-speed signals, and that's just the tip of the iceberg. There's no time to go into that here, but it's just a very, very important criteria. As important is EMI noise susceptibility. How susceptible are your circuits to other EMI generated noise? For example, with an SDR, if you are transmitting on some frequency that might interfere with some digital logic, that is a big issue and may render the board unusable. So you have to isolate all of that RF energy that's generated from the SDRs from the digital logic. You also have to shield the SDR circuitry from the EMI generated on the board. And there are certain kinds of chips that are particularly sensitive to EMI generated noise. For example, GPS receivers. And in the next slide, you'll see that. This is a portion of one of those boards that you saw earlier, where there is a shield over one of these U-Blocks, UBLOX. They're a Swiss brand of GPS and other kinds of radio receiver chips. So there's a U-Blocks Neo M8 series GPS chip underneath this shield. We found that we had to mount this chip in a way and shield it in a way so that it would not be interfered with from the digital logic from this card. And in particular, it's pretty well known that USB 3 interfaces interfere with GPS receivers very, very intensely. So we had to make this work. And we found by shielding this and putting this on the opposite side of the board through several ground planes away from the USB 3 lines that we solved that problem. And we also chose a GPS chip that does not have a built-in LNA. We recommended to this customer they have an LNA out at the antenna, and we power that through a bias T. And that way, the lower signal levels on this GPS chip made it less interference prone than a GPS chip that had the LNA built in. And the other half of that story is when we interfaced the USRPs into the system, we used very short runs of shielded, actually micro coax transmission lines from the USB 3 connectors on the USRPs into our system, okay? And we mounted the USRPs in an electrically isolated way so it did not create a ground loop. And all the ground points are tied back through the USB 3 lines back at the USB 3 connectors at one point. If we had tied the USRPs into the ground plane electrically through this case, instead of using these nylon screws, we would have had a ground loop, which would have made it much more susceptible to interference and actually made a little loop antenna for ourselves. We didn't want to do that. As I was just mentioning, we always like to put LNAs, not only for the GPS, but for the SDRs out at the antennas. Anything you can do to raise the signal level into the SDR before it gets exposed to that high level of digital logic noise, if you will, the better off you are. And what we do is we always provide bias T circuits and provide either 5 volts or 12 volts out at the antennas so that an LNA can be powered. Now, often LNAs are frequency specific, or sometimes they need to be gain controlled, and that means the CPU has to have GPIO signals in order to control those parameters. And in this particular example on this board, we don't do that, but we have done that on others. Here's an example of the bias T circuit that we provide out to that GPS with jumper selection for voltage. Similar to the LNA, if you have a power amplifier, you need to do similar kinds of things. Locate those externally from the main board, away from the digital logic, so that power doesn't interfere with the digital logic in reverse, and provide whatever power you need out those same connectors. Grounding strategy is something that is a huge issue. It can be a huge issue. It's a huge topic. You can spend hours or days. You can spend whole courses on this. But in general, there's a concept of an earth ground, literally the earth and the ground in the earth, a chassis ground, the metal chassis around the enclosure, and a signal ground that references all of your signals on the board. And from a DC point of view, all these can be the same and should be the same. But from a signal perspective, a high frequency, all are quite different. And you need to ensure that all three reference the same static DC voltage. And how you do that is critically important. I won't go into all the examples and ways to solve this problem, because as I said, we could take hours on this particular topic. But one example of one thing that we do, how you join the signal ground to the chassis ground is important for EMI noise generation as well as susceptibility. And it often has to be determined. You can design it correctly in the beginning, but you often have to fine tune it in the field, particularly in FCC testing. And what we do is we put little 0 ohm resistors that tie between signal ground and chassis ground. This little mounting hole, this gold plated mounting hole, is where you would typically pick up a chassis ground. And that R54, the 0 on it, that's a 0 ohm resistor that ties into signal ground. We have one of these on every mounting hole, and we experiment by removing these and measure the noise that we generate in order to generate the optimal grounding situation. Environmental issues, ingress protection standards are always important. Things sometimes have to be immersion or splash proof. We mentioned that earlier with fans. Often a rugged environment's needed because embedded products generally work in an environment that's more rugged than your desktop or laptop. They have to be vibration and even drop proof at times. One small example of how to help this vibration proof is, for example, screw down these little add-in boards. This is a little mini PCIe card for Wi-Fi. And in most laptop and consumer environments are little clips. You push that in, you clip it in. That's not sufficient in embedded environments, so we provide little studs and screw it down. Likewise, how you mount internal cables is very important. The little micro USB, I think it's micro B USB connectors on these USRPs are notorious for coming loose in the field. They're tiny little connectors with very little insertion force and very little extraction force, and they wiggle loose or they wiggle out of connect. So we designed a cable with a manufacturer that actually provides a spring of kind of a coiled spring kind of action. So it keeps that cable inserted very positively. I won't dwell on this, but field updates and crash recovery, they have to be sort of designed in the same thought. You know, how you want to update your product in the field. Do you ever want to update the OS? Do you want to update your application? Do you want to update data? Do you want to download data? How do you want to recover from crashing? Do you have an extra set of images on your SSD in a very protected area that you can reload if things do go awry, either in updating or in operation? So that's something that needs to be thought of from the very beginning. And there's always certifications, UL, FCC, CE, there's a bunch of others. You have to design the product to pass. You can't design the product to be functional and hope it passes. You have to design from the beginning to ensure that it will pass, or give yourself enough options like those little 0-ohm resistors so that you have some flexibility to allow it to pass. And these things cost a lot of money to get them tested, and they take a lot of time. So it's a very important part of the product life cycle. And it's worth mentioning now, parts availability. Ever since COVID, there's been a real problem in getting many parts. We find that we're competing with auto manufacturers and every sorts of manufacturer of getting parts. And you've got to, what we do is we take an approach of all of our products are designed around as few unique parts as possible, and try to have as much of a 2-year parts inventory as we can. It's not perfect. It's very difficult to do that. And all of our manufacturing is done with a contract manufacturer in the United States. They're out in Oregon, our main CM. And we work closely with them, with their inventory levels and our inventory levels, to make sure that we can produce product.
Thank you all for listening and for all your patience. So I think we're going to have time for some Q&A right now, and I look forward to that.
All right. Thank you, Jeff. And let's give Jeff a round of applause.